So let us look at an example on Parseval formula. So let us consider a function f of x equal to x squared on minus pi pi. It's an even function extended as a 2 pi periodic function outside of minus pi pi. So let us calculate the Fourier coefficients of this function f of x. A naught is 1 upon 2 pi integral minus pi to pi x squared dx. One can immediately evaluate the integral and the answer we get pi squared by 3. Of course, there's a 1 upon 2 pi factor thrown in, and so that's why you see a pi squared and not a pi cube. 1 pi cancels out. Obviously, Bn is 0. Why is Bn 0? Bn is 0 because the function is an even function and sine nx is an odd function. So integral fx sine nx from minus pi to pi will be 0. Alright, now go to an. An is 1 upon pi integral minus pi to pi. Again it's an even function, so an will be 2 upon pi integral 0 to pi x squared cos nx dx. Now we write cos nx as d dx of sin nx with a 1 upon n thrown in. So we get 2 upon n pi integral 0 to pi x squared d dx of sin nx. Integrate by parts. When you integrate by parts, the boundary terms will cancel out because sin nx vanishes both at 0 and at pi. And the only other term that will survive is the integral term with the derivative shifting from the sin nx to x squared. So we get minus 4 upon n pi integral 0 to pi x sin nx dx. One more integration by parts. Sin nx should be written as d dx of cos nx divided by n. You do that and finally you get an as 4 times minus 1 to the power n upon n squared. So now we have the a naughts, we have the an and we have the bn. What does Parseval formula give you? 1 upon 2 pi integral minus pi to pi mod fx squared dx. So mod fx squared means x to the power 4. So we get 1 upon 2 pi integral minus pi to pi x to the power 4 dx equal to mod a naught squared. But remember that a naught was what? A naught was pi squared by 3. So a naught squared is pi to the power 4 upon 9 plus the infinite series 1/2 summation n from 1 to infinity mod an squared plus mod bn squared. Bn is 0. We are left with summation n from 1 to infinity mod an squared, that is 16 by n to the power 4. Now we must calculate this integral 1 upon 2 pi integral minus pi to pi x to the power 4 dx. You calculate that integral and you subtract off the pi to the power 4 by 9 and do the simplification. You get the beautiful formula 1 plus 1 upon 2 to the power 4 plus 1 upon 3 to the power 4 plus etc. equal to pi to the power 4 upon 90. Now if you have worked out the exercises in the previous module on pointwise convergence, you would have obtained one formula 1 plus 1 upon 3 squared plus 1 upon 5 squared plus etc. as pi squared by 8. It's an easy exercise for you to check that 1 plus 1 upon 2 squared plus 1 upon 3 squared is pi squared by 6. How do you do that? 1 plus 1 upon 2 squared plus 1 upon 3 squared etc. Separate the odd terms and the even terms. 1 plus 1 upon 3 squared plus 1 upon 5 squared etc. And then it will be 1 upon 2 squared plus 1 upon 4 squared plus 1 upon 6 squared etc. And so take a 1/4 common and you will get the answer. So you will get pi squared by 6. Please do this exercise. It's a very instructive exercise. So now we have found the sums of the reciprocals of the squares of the natural numbers and the sum of the reciprocals of the 4th powers of the natural numbers. Pi squared by 6 and pi to the power 4 by 90. Now let us go a step further and look at what are Bernoulli polynomials and Bernoulli numbers. This is a very classical part of mathematics. It goes back to James Bernoulli. So we define the Bernoulli polynomials inductively. It's a sequence of polynomials b and x. b naught of x is defined to be 1, and they are defined recursively. Bn prime of x is n times Bn minus 1 of x when n is 1, 2, 3, etc. So for example, when I put n equal to 1, what do I get? B1 prime equal to 1. So B1 will be what? X plus c, where c is a constant of integration. How do you find the constant of integration? Look at the third displayed equation on the slide. Integral 0 to 1 bnx dx is 0. So the value of the constant must be minus half. So b1 of x must be x minus half. Similarly, you can calculate b2, b3, etc. b2 prime x equal to 2b1. So you know b1 already. You can find b2. There will be a constant of integration. Use the integral formula, namely the third displayed equation. Integral 0 to 1 b2x dx is 0. So keep going. So the exercise is calculate the first few Bernoulli polynomials, and I already started you with this exercise. Now put x equal to 0. The numbers b and 0 are called Bernoulli numbers. Now you might ask, what is the significance of Bernoulli polynomials and Bernoulli numbers? Let us see. These are two very classical formulas. You see the first one, it goes back to James Bernoulli in his monumental treatise called Ars Conjectandi, which was written in 1713, which is more than 200 years old. So 1 to the power p plus 2 to the power p plus etc. plus n to the power p. There's a closed formula for that, closed expression for this series. The sum of the series is 1 upon n plus 1 into bp plus 1 at n plus 1 minus bp plus 1 at 0. So you can check this result by putting p equal to 1, by putting p equal to 2. You already know that 1 plus 2 plus 3 up to n is n into n plus 1 by 2. And you already know what is b2. So please check the correctness of this formula for n equal to 1, for p equal to 1 and 2 respectively. The second equation is more interesting, equation 2.8 in the display. It's a result that goes back to Euler, 1736. 1 plus 1 upon 2 to the power 2p plus 1 upon 3 to the power 2p plus etc. equals minus 1 to the power p plus 1, 2 pi to the power 2p, b2p of 0 upon 2 into 2p factorial. So put p equal to 1 and put p equal to 2. And look at the right hand side 2.8. See whether you get pi squared by 6 and pi to the power 4 by 90 respectively. So check the correctness of 2.8 for p equal to 1 and p equal to 2. The brothers James and John Bernoulli tried in vain to obtain 2.8 for p equal to 1. They tried very hard to find the sum of 1 upon 2 squared plus 1 upon 3 squared plus etc. in closed form. Unfortunately, James Bernoulli did not live to see this equation 2.8, in which the numbers bearing his name feature so prominently. As a next exercise, let us define the function f of x equal to x into pi squared minus x squared. Extend it as a 2 pi periodic function on the entire real line. Calculate the Fourier coefficients a0, an and bn. This time you are going to get the an's will be 0. This is an odd function. X into pi squared minus x squared is an odd function. So the an's will be 0. The a0 will also be 0. Only the bn's will be non-zero. Calculate the bn's and apply Parsevals formula to determine the value of 1 plus 1 upon 2 to the power 6 plus 1 upon 3 to the power 6 plus etc. And verify whether the result you obtained is in agreement with equation 2.8 that you see displayed. These are some very instructive exercises for you to try it out. Now let us go to the classical problem of Descartes. It actually goes by the name of Diderot's puzzle. It's an ancient puzzle. It's a beautiful application of Parseval's formula. And this was the promised application to a classical problem in geometry. So what is the problem? It is called the Isoperimetric problem. So let us look at Theorem 19. Of all piecewise smooth closed curves with a given perimeter, the circle encloses the maximum area. So take for example a square and try to crush the square into a parallelogram which is very thin. The area will become smaller and smaller, and the square, the original square, had the maximum area of all possible deformations. Now compare the area of a square and the area of an equilateral triangle. Take a square and an equilateral triangle with the same perimeter and see which one has larger area. Take a hexagon, a regular hexagon which has the same perimeter, and find the area of the hexagon. I think you should experiment with these things and try to convince yourself of the correctness of Theorem 19, namely of all possible smooth closed curves, piecewise smooth closed curves with the same perimeter. The perimeter is fixed. What is maximized? The area. It's an intuitively very appealing, and probably you are convinced that this is correct. But we would like to see a very clear mathematical proof, a rigorous argument. Now we can do the other way around. We can fix the area and see how to minimize the perimeter. It's called the dual problem. Theorem 20. Of all piecewise smooth closed curves enclosing a given area, the circle has the least perimeter. So this time the area is fixed, the perimeter changes. So the circle minimizes the perimeter. Now this is an isoperimetric problem in the plane. What will be the isoperimetric problem in space? No prizes for guessing. So take all possible bodies which have fixed surface area. The sphere will maximize the volume. Or the analog of Theorem 20, if you fix the volume, then of all possible bodies with a given volume, the sphere will minimize the surface area. So the theorem generalizes to higher dimensions in a very obvious manner. The three-dimensional version, where the sphere minimizes the surface area, is very significant. This is what is responsible for the shape of soap bubbles. When you blow soap bubbles, the soap bubbles are spherical. The reason for this shape, the spherical shape, is because the surface area is minimized, and so the stable configuration is a sphere. Because of the minimization of the area, the surface tension is minimized. Now let's come to a very beautiful analogy given by George Polya in his delightful book Mathematics and Plausible Reasoning, Princeton University Press, 1954. And it's a multi-volume book. The first volume is Induction and Analogy in Mathematics. So look at the analogy that he gives for the spatial isoperimetric problem. He says, with a little knowledge of physics of surface tension, we could learn the isoperimetric theorem from a soap bubble. Yet, even if we are ignorant of serious physics, we can be led to the isoperimetric theorem by quite primitive considerations. We can learn it from a cat. I think you have seen what a cat does when he prepares himself for sleeping through a cold night. He pulls his legs in, he curls up, and in short, makes his body as spherical as possible. He does so Obviously, to keep warm, to minimize the heat escaping through the surface of the body. The cat, who has no intention of decreasing his volume, tries to decrease his surface. He solves the problem of a body with a given volume and minimum surface area, making himself as spherical as possible. He seems to have some knowledge of the isoperimetric theorem. You will see this quotation on page 170 of Polya's book. I urge you to take a look at this book and see the other interesting analogies which Polya gives, and Polya gives various proofs of the isoperimetric theorem. What we are going to do here is to look at a proof of the isoperimetric theorem which was given way back in 1902 by Adolf Hurwitz. So let us take a piecewise smooth closed curve parametrized by arc length. We can always parameterize a curve by the arc length measured from a fixed point along the curve. Let us assume that the total perimeter of the curve is L, capital L, so that the arc length parameter S will run from 0 to capital L. What is the area of the closed curve? The area of the closed curve is given by an integral. It's a line integral x dy. But the line integral is basically 0 to L x dy by ds ds. X is a function of s and y is a function of s, and s runs from 0 to L. How is it true that A is integral x dy? Think of applying the Green's theorem, the classical Green's theorem. The line integral of p dx plus q dy. What is that equal to? The double integral over the interior of the curve, del q by del x minus del p by del y dx dy. Here p is 0, q is x, del q by del x minus del p by del y is 1, and so you get the area. So the area is integral x dy, or integral from 0 to L x dy by ds ds. Now let us make a change of scale and a shift of origin, so that I want to apply the formulas that I had derived. So let us make the parameter change in such a way that t equals 2 pi s upon L minus pi. The minus pi is done so that the interval goes from minus pi to pi. So t runs over the interval minus pi to pi when s runs from 0 to L. Then the area formula is integral minus pi to pi x dy by dt dt. So for the perimeter we have dx by dt the whole squared plus dy by dt the whole squared, which is ds by dt the whole squared, right? And what is ds by dt? ds by dt is basically L squared by 4 pi squared, because when you parameterize a curve with the arc length, the speed of the curve is 1. That's how we get that formula L squared by 4 pi squared, which is more conveniently written as 1 upon 2 pi integral minus pi to pi dx by dt the whole squared plus dy by dt the whole squared dt, and that is the same as L squared by 4 pi squared. Some of these details will be written out in the text that will accompany these lecture slides. Meanwhile, it's an exercise for you. I urge you to figure these things out without looking at those texts. So that's equation 2.10. Now let us write the Parseval's formula, and what do we get? Let's apply the Parseval's formula to 2.9 and 2.10. What do you get? The nth Fourier coefficient of xt is, let us say, an and bn, and the nth Fourier coefficient of yt is, let us say, cn and dn. Then for the area integral, what do you get? It's x dy by dt. So you must write the Fourier series for x and the Fourier series for dy by dt. So write down the Fourier series for y, differentiate term by term, you get another Fourier series. When you differentiate cos nx and sin nx, you pick up a factor of n. You multiply the two series and you integrate term by term. Cos nx, cos mx, integral will be 0 when n is not equal to m, and so on. What you will get is the formula A equal to pi times summation n from 1 to infinity n times an dn minus bn cn. You have to fill in the details for this expression for A. Similarly, for the perimeter, L squared equal to 4 pi squared, but there will be a factor of half coming in from the Parseval formula. You get, you're differentiating x and you're also differentiating y, dx by dt the whole square, remember, and dy by dt the whole squared. So all terms will have an n and you're squaring it. So it will be n squared into an squared plus bn squared plus cn squared plus dn squared. So you subtract L squared minus 4 pi a will be what? It will be 2 pi squared, common factor, summation n from 1 to infinity, n squared into an squared plus bn squared plus cn squared plus dn squared. Subtract of minus 2n into an dn minus bn cn. Complete the squares. When you complete the squares in the most obvious way, you get nan minus dn the whole squared, nbn plus cn the whole squared, plus the last term, which is interesting, n squared minus 1 into cn squared plus dn squared. Now, all the terms in this expression are non-negative because n is running from 1 to infinity, remember. So, all the expressions are non-negative. So, L squared will be bigger than or equal to 4 pi a. So, L squared is always bigger than or equal to 4 pi a, and the maximum value of the area is L squared by 4 pi. So, a is less than or equal to L squared by 4 pi. So, the maximum value that a can ever attain is L squared by 4 pi. And this value is certainly attained by the circle. This value is certainly attained by the circle. What we need to show is that if this value is attained, then it is a circle and nothing else but a circle. The circle maximizes the problem, that is certainly the case. No other curve will maximize it. So, if L squared is equal to 4 pi a, then what happens? Then in the previous slide, the left hand side is 0. So, this summation must be 0 and every term must be 0. The only way every term can be 0 is n has to be 1 compulsorily and nan minus dn must be 0 when n is 2, 3, 4, etc. And bn plus cn must be 0 when n is 2, 3, 4, etc. And you get a1 equal to d1 and b1 equal to minus c1. So, we know that the cn's must be 0, the dn's must be 0 and the an's and the bn's have to be 0 beyond n equal to 1, that is for n equal to 2, 3, 4, etc. So, the Fourier series for xt and yt simply has only the constant terms and the a1, b1 and c1, d1 term, but c1 has been expressed in terms of b1, d1 has been expressed in terms of a1. So, you get the Fourier series x of t equals a naught plus a1 cos t plus b1 sin t and yt equal to c naught minus b1 cos t plus a1 sin t. So, what is this curve xt comma yt? It is a constant a naught comma c naught plus cos t into a1 comma minus b1 plus sin t into b1 comma a1. Again, xt comma yt is a constant vector, whatever it is, plus cos t times a vector plus sin t times another vector. What is coefficient of cos t? a1 comma minus b1. What's the coefficient of sin t? b1 comma a1. So, we are in the situation u cos t plus v sin t, where u and v are two orthogonal vectors of the same length. Prove that it's a circle. The curve u cos t plus v sin t when t runs from 0 to 2 pi describes a circle provided u and v are orthogonal and u and v have the same length. We have proved that the only curve that maximizes the area is the circle. Okay, and the proof of the theorem is complete. Now we shall move on to another aspect in the next lecture.